Okay, I'll share the screen soon. Yeah, good morning, everyone. So this is the theorem which we had proved last class, that the Bt is the standard one-dimensional Brownian motion, and T1, T2, Tn, these are fixed increasing time points in increasing order. Then this random variable Bt1, Bt2, Btn, it's a probability density function of this n-dimensional random variable we had expressed in terms of the one-dimensional probability density function of Bti minus Bti minus 1. And we know that Bti minus Bti minus 1 has the normal density with mean 0 and variance Ti minus 1. So Fxi denotes that. So we have given an expression of this n-dimensional probability density function of the n-dimensional random variable in terms of these one-dimensional probability density functions. Of course, we had also said something more about it, that the exact distribution of this can be expressed. This is an n-dimensional normal distribution. Anyway, so today we will use that statement of the theorem 1. Yeah, this to prove Markov property of Brownian motion. Yeah. We will not really mention what is Markov property till the end in this context. Of course, you can easily guess that. So, yeah, to start with, let T1, T2, Tn and Tn plus 1, let these be n plus 1 time points in increasing order. And f sub I denotes the probability density function of Bti minus Bti minus 1. So you know that this Fi is the density function of the N0 Ti minus Ti minus 1 distribution, the not one-dimensional normal. T0, of course, is taken to be 0, so that the notation is consistent. Okay. And we denote by F super n the probability density function of that Y super n, we denote like that, so that is notationally convenient. That is our Bt1, Bt2, Btn. And in the same manner, F super n plus 1 denotes the probability density function of this n plus 1 dimensional random variable Bt1, Bt2, Btn, Btn plus 1. So what we are going to do is the conditional density function of yn plus 1 given yn equal to something. That is what we are going to look at. So that is why we took n plus 1 time points to start with. And then if you are given the value of this, that it takes a particular value in Rn, on the basis of that, what can you say about the probability density function of yn plus 1, the conditional probability density? That's going to be quite simple. You take the density function of this and then divide it by the density function of that and so on. But then one has to be a bit careful. Please note it down if you want to. So by yesterday's theorem, we have these expressions. Yesterday's theorem applied to n random variables here. This is n plus 1. So these two are, they are identical up to this point. And the difference comes here. Not only that, each of these Fi is the probability density function of a one-dimensional normal distribution. And from our knowledge of one-dimensional random variables, normal random variables, we know that that density function is strictly positive on the entire real line. Fi strictly greater than 0 on the real line. So consequently, if you look at this expression, F1 at Y1 will be strictly positive, F2 at Y2 minus Y1 will be strictly positive, and this will also be strictly positive. Consequently, this entire product is strictly positive for every Y1, Y2, Yn in Rn. So by the first equation in this, which is namely this equation, we now get that the left-hand side of this is strictly positive for every point in Rn. I hope that's clear. So the next step, we have to divide this expression by that expression. So that will just give us this. And cancellation is allowed because this guy is strictly positive. Please note it down if you want to. Okay. So now let Y1, Y2, Yn in Rn be fixed. Then using the second equation, that is this equation, so we are going to divide this expression by that expression. The conditional probability density function of just that Bt n plus 1 given this, the nth component of that Yn plus 1 given the first n components. First n components is equal to Y1, Y2, Yn. So that thing is, by definition of the conditional probability density function of this, it is, so this is the notation for conditional probability density function of Bt n plus 1 given this guy. So this is the notation for the conditional density function. So by definition of this, which we have seen earlier in this semester, in the first few classes, this is equal to the joint or the probability density function of Bt1, Bt2, Btn and Btn plus 1 at this point, Y1, Y2, Yn and Y, divided by the one corresponding to n. So since this is strictly positive, this expression is valid for every Y1, Y2, Yn and of course Y in R. So what you get is from that, the second equation in this thing, it is F sub n plus 1 at Y minus Yn. Now recall this Fn plus 1 from your, Fn plus 1 is the probability density function of Btn plus 1 minus Btn. So therefore, we have this Fn plus 1 at this is precisely the density function of Btn plus 1 minus Btn evaluated at y minus yn. Please note it down, be carefully all these kind of symbols. Try to see that this is at a slightly lower level than this y and so on, so that there is no confusion. So basically, the argument is very, very simple. It is just that using that theorem, we take the Bt1, Bt2, Btn and Bt1, Bt2, Btn, Btn plus 1. And that denote that n dimension, this corresponding multi-dimensional density function by f super n and f super n plus 1. And our purpose is to talk about conditional density of Bt1 given Bt1, Bt2, Btn equal to some vector in Rn. So by yesterday's theorem, we get f super n equal to this and f super n plus 1 equal to this. And each of these fi's are strictly positive. Consequently, this f super n at any y1, y2, yn super is strictly positive. So using that information, we want to find the conditional probability density function of Btn plus 1 given Bt1, Bt2, Btn equal to some vector. And that is precisely this. Please note it down carefully. Yeah. So now we are sort of going to look at Markov property. That is something like we have to say that in this expression, certain things are irrelevant concerning the past. So here up to n minus 1 will not be relevant. So what we suspect is that this conditional probability density function of Btn plus 1 given Bt1, Bt2, Btn is going to be perhaps the same as conditional density function of Btn plus 1 given just Btn alone. And we have kind of indication here. Okay. Now, by very similar arguments, instead of taking n plus 1 time points, just take 2 time points, Btn and Btn plus 1. The last 2 time points which were relevant in the, which you came across in the earlier discussion. So supposing here you had taken Tn and Tn plus 1 only. Forget about all the other earlier things. Then instead of this Bt1, you will have Btn and that Btn plus 1. So here you will have this term, of course, look here. Here it will be corresponding to Yn and Yn plus 1. This will be there. And instead of all these things, it will be substituted by something similar to this, just the probability density function of Bt1 evaluated at that Yn. So it is a simple exercise for you. So that is why we have said verify. Verify that the probability density function of the two-dimensional random variable Btn and Btn plus 1 is given by, this is the joint density of this random variable, at Yn comma y is f Btn Yn multiplied with f Btn plus 1 minus Btn y minus y. We are taking just two time points. Only thing is we are calling the time points as Tn and Tn plus 1. So similarly, again verify the conditional probability density function of Btn plus 1 given Btn equal to Yn. That would be the joint density of Btn plus 1, which is given by this, divided by just the density of Btn at Yn. So you have to divide this by f Btn Yn, as we had done in the earlier page. So this will get cancelled. This is strictly positive. So you will get, once this goes away, you will, this will remain. That is what we have. Please verify each and every step. Also, while noting it down, be careful about all this notation. These are subscripts. This entire thing is a subscript. I had to watch out while typing, but here again, I have made some more error. One parenthesis is missing here. Or I should take away this parenthesis. So now you compare what we had denoted by this triple of this symbol, and in the earlier thing, the double that symbol. The right side of both are same. Consequently, the left sides are also same. Please note it down. Okay. Therefore, using these two equations and observing that the right sides of both these equations are the same, we get the left sides are also the same or equal. That is, the conditional probability density function of Btn plus 1 given BT1, BT2, BTN equal to this point Y1, Y2, Yn, evaluated at a point Y in R, is same thing as the conditional probability density function of Btn plus 1 given Btn equal to Yn evaluated at Y. So whatever information given here concerning BT1, BT2, Btn minus 1 become irrelevant. That is the crux of the Markov property, as you have seen in your Markov chains and also the earlier in the continuous time Markov chain and so on. That is what I have written down in words now. Conditional probability density function of Btn plus 1 given Bt1, Bt2, Btn equal to Y1, Y2, Yn is the same as the conditional probability density function of Btn plus 1 given Btn equal to just the last of this guys. So this is a fairly simple, straightforward calculation, but the only thing is the notation is somewhat irksome, irritating. Though the notation is perhaps the best possible. Sadly, it makes the things quite clear, but only thing is there are a lot of symbols involved which you have to sort of wrestle with. Okay, now using this, we will put these things in a shape where you can easily sort of see the familiarity with the earlier cases. Okay. So in view of all these things which we have done, suppose an integer k greater than or equal to 1 is fixed. Now we will change the kind of the notation we have given for the time points. Let the time points be R R1, R2, Rk, S and T. So there are k plus 2 time points. And k plus 1 real numbers, let's say Xi1, Xi2, Xk and X. And also a set A, a nice set in A, Borel set. So we are going to talk about probability that the Bt takes value in K given P at all these time points equal to this. And we will see that these things do not matter. That precisely is your Markov property. Okay. So we mentioned here, we want to find probability Bt takes value in A, in the set A, given BR1 equal to Xi1, BR2 equal to Xi2, BRK equal to Xk, and Bs equal to X. But what we have seen in the early part of the semester, this kind of probability is same thing as you integrate over A, y times you take the conditional probability density function of Bt given Br1 equal to Br1, Br2, Brk, Bs equal to this K and 1, K plus 1 dimensional vector, and this is a probability density function. For all these things fixed as a function of y, this is a one-dimensional probability density function as a function of y. And also these things make sense. We have seen earlier, whatever may be the Xi1, Xi2, Xk and X, this conditional density is well defined. And what we have just proved here, using that, this conditional density is same thing as conditional density of Bt given Bs equal to X, the last one. So therefore, this integral, you can replace this conditional probability density by this conditional probability. But what you have here is just this guy. Just like you came from here to here, no, this is the reverse direction. So that is conditional probability that Bt takes value in A given Bs equal to X. So for that means this information Br1 equal to Xi1, Brk equal to Xk, that is not relevant in finding this. In finding this expression, that is not relevant. Just the last one alone would do. And that happens for every Borel set in R and every X in R and every T and S. So T is considered the future time point here, S is the present, and all these things are in the past. So forgetting the past. That's a Markov property. Please note it down. Yeah, so we are just saying that equating the first and last and writing it. And denoting it by this bullet, this equation. So this is precisely the statement of the Markov property for this one-dimensional Brownian motion B. So Bt is a Markov process. The standard one-dimensional Brownian motion is a Markov process. So that is the conclusion. But that is nothing surprising, no? We know that Brownian motion has the independent increment property. So that is a stronger property than Markov property. property. As you have seen earlier also, the random walk is certainly a Markov chain, but a Markov chain need not be a random walk. So you can have Markov processes which don't have the independent increment property. You can give examples from Markov chains itself. Whereas any Markov chain where the independent increment property is there, that is certainly Markov. As the independent increment property is stronger than the Markov property, this should be not that than, stronger than. Typo, please correct. In other words, this is something intuitively obvious, that is increment property is stronger, therefore the Markov property should hold. But what we have done is basically to sort of taken care of all the nuts and bolts, proved it using that theorem which we had proved last class. As a simple, it is a simple concept, derivation using that. Okay. Now let us look briefly at what is called Brownian motion with drift. So obviously this such a process will not be a standard Brownian motion. So define this B hat process by P hat of t is Pt plus m times t. M is a constant. So this is called Brownian motion with drift, and the m is called the drift parameter. So in addition to the Brownian motion component, there is also a drift linear motion. So you can easily see that expectation of B hat t is going to be expectation of this plus expectation of this. Expectation of this is 0. Well, expectation of this is a constant, so it is m times t. So expectation of B hat t will be mt. So therefore, the distribution of this that will not have mean 0, it will have mean mt. So there should be the braces here corresponding to this. So you can easily check that this B hat t has continuous sample paths. That is very obvious. You have to, next is you show that B hat t also has the independent increment property. That again is not difficult. Also, so we have seen that B hat t has expectation mt. B hat t, the variance will be just t. Because you know that the random variable, and if the random variable is translated by a constant. They have the same variance. So that is what you have seen in your first course in probability. So B hat T plus S minus B hat S as the normal distribution with mean MT and variance T. Of course, this is a more involved exercise. I would suggest you do it. The Markov property also holds for B hat. Of course, since in this part you are asked to prove that it has independent increment property, this is not surprising. But as we had done for the standard Brownian motion, you try to do something similar with taking care of all the appropriate modifications. So to sort of do this, first of all, you have to see how will the analog of the theorem 1 will look like for the Brownian motion with drift. So any question or comments, or you want me to go back to any of the slides?
So,
No, okay. So in that case, we will end the session for today. Yeah. And yeah, we will meet on Wednesday. Okay, take care. And okay.
thank you, sir.
Yeah, thank you very much. Yeah.